Okay, so next topic is water. We're going to talk about water. But the topic is kind of water. We're going to use water, and we are going to talk about water, but we're going to use water as our opportunity to talk about bonding. We'll also use it to kind of keep muddling our way through how we're going to approach a lot of the topics that we are going to talk about. So, water is a molecule that has both covalent bonds and hydrogen bonds. We'll talk about how that works and where they are in a minute. Hydrogen bonds are something that can vary in strength. They're typically a weak bond, but they typically travel in numbers, getting some strength out of them that way. So, we're going to talk about bond strength, what causes the variations in it, and what we get from that bond strength. We're also going to talk about partial charges. So we're going to start out, actually, you know what, we'll start on a different diagram. We'll start out on this diagram, just a single water molecule. So a water molecule is an oxygen with two hydrogens attached through covalent bonds. So in general chemistry, you talked about covalent bonds where you have an actual sharing of electrons. So back in Gen Chem, when you were drawing your atoms and you were drawing orbitals around it, you felt like you were drawing planets in the solar system, and you were putting your electrons in your orbitals, and then you were looking at the orbitals and were they full, not full, depending on what was going on, what could that atom share electrons with to form a bond? You were looking at covalent bonds there. So a covalent bond is really a true sharing of electrons kind of a bond. So that's what we have going on here. We have the oxygen sharing electrons with two hydrogens. But when we say sharing, sharing is not necessarily an equal sharing. And it's really easy to forget that. We think sharing, we think 50-50. But let's think about this. Let's say you and I decide we're going to save some money and we're going to buy a biochemistry book together and share it. And we decide this is a good idea. So you do that with me. I'll keep the biochemistry book most of the time. You can have it, Tuesday night between 7 and 9. So you have it sometimes. We're sharing. I don't know what you're complaining about. We're sharing. But it's a very unequal sharing. So that's the point. Oxygen kind of operates like that. Oxygen is a big electron hog. And I'm saying that very much on purpose because we're going to see the effect of oxygen being a big electron hog multiple times. So what I mean by that is oxygen's keeping the lion's share of the electrons. So that's going to leave the oxygen a little bit negative. Since it's keeping the lion's share of the electrons, it's doing it at the expense of the hydrogens, leaving them a little bit positive. So really what I should be saying is that the oxygen will have a partial negative charge, the hydrogens will have a partial positive charge. That determines the shape of the water molecule. So let's talk about how that happens. So in this diagram, I have my oxygen as the red or brown blob. My hydrogens are the bluish purplish blobs. So in one water molecule by itself, I have the oxygen keeping its partial negative charge, the hydrogens keeping their partial positive charge. So that's my one water molecule. But nothing happens in a vacuum. So what happens then, because of these partial charges, is each oxygen will hang out with another hydrogen. What I mean by hang out is it's not sharing anything. It's an attraction between this partial negative charge and those hydrogens of two other water molecules, partial positive charges. Then each of its hydrogens will hang out with two more oxygens. That hanging out again is a hydrogen bond, an attraction. that's resulting from the partial negative charge on the oxygens and the partial positive charges on the hydrogens. So we've got one water formed, let's say one oxygen married to its own two hydrogens and hanging out with two more. We have each oxygen married to its hydrogens hanging out with another. So married to its two hanging out with another. This isn't biochem getting juicy. We have polygamy, we have hanging out, we have everything. So that causes kind of a balance that causes the shape of the water molecule. So let's look at that. We have an oxygen covalently bonded to two hydrogens. So we have our partial negative charge, our partial positive charges. So we've got a couple of things going on that cause the shape of this molecule. So much of our chemistry and our shapes and our structures come from balances of charges. And what I mean by that is comes from like charges pushing away from each other, unlike charges pulling towards each other. So let's erase some stuff here just to kind of have room to work. So if we look at that one water molecule individually first, based on like charges wanting to be away from each other, unlike charges wanting to be together, that one water in a vacuum should be linear because these two hydrogens want to get away from each other. But there's more to it than that. It's a balance. It's always a balance. What's going to happen is we have the two hydrogens that would like to push away from each other, but these two oxygens are pulling those hydrogens towards them. So we got the push away here, we got the pull here. But then we got another hydrogen up here, it wants to push away. So we've got all this push-pull kind of thing going on. The balance of the pushes and the pulls gives us a bond angle here of about 106 degrees. Not important at this point that you know that number. What is important is that you get the concept of this pushing and pulling that gives you that angle. That angle is the result of basically the pushes and the pulls. The reason we're spending the time on this right now is not so much about the bond angle of water being that important, but this push-pull idea is going to be something you're going to see over and over through the course. It's kind of like back in organic chemistry, when you looked at any question that was why about a structure, there were two answers. And no one told you this during organic. It was one of those things you figured out after. But if the why was, why is something pulled together, it's going to be hydrogen bonding. Why is something pushed apart? It's going to be steric effects or steric hindrance. Unlike charges want to pull together, like charges want to push apart. Parts of molecules want room. So that's our steric hindrance. They want to spread out and have room. So kind of saying the whole thing very, very casually, but when it comes down to it, that's really how it works. So when we were talking about chemical bonds, covalent bonds are the sharing of electron kind of bonds. So that's what we're using to form one water molecule. So when we talk about that sharing, when we say it's a sharing, but it's not an equal sharing, what we're talking about is a polarity. So that unequal sharing that results in those partial charges is a polarity. So we have a polar covalent bond. That leaves us with the oxygen staying a little negative, meaning we have a small localized negative charge around the oxygen. The hydrogens stay a little bit positive. We have a small localized positive charge around the hydrogen ions. So, or the hydrogens. So that's really what we're talking about here. Okay, so our polarity is what we were talking about. The partial charges, making that sharing an unequal sharing. So unequal or uneven sharing of electrons around the hydrogen and the oxygen gives us a polar covalent bond with a bond angle of 104.5 degrees. The other thing is, let me go back, this molecule forms a tetrahedron. So we have these four corners that are the four other hydrogens or the four other water molecules, four other hydrogens hanging out, forming a tetrahedron. So you'll see here, water has a tetrahedron shape. The oxygen is in the middle of four hydrogens, two covalently bonded, two connected through hydrogen bonds, making that tetrahedron shape. So a little bit of an odd term on something with one oxygen and two hydrogens, three components, but it's the four hydrogens hanging out or bonded to that oxygen. So water has some characteristics, and we'll talk about them. Donates the unpaired electrons to electrophiles. We'll talk about the relevance of that later when we get to some of the processes that we use that in. Water is important in pretty well all biological pathways. So we're going to see water playing a role in everything, whether we're talking about carbs, fats, proteins, whatever we're going to be doing. Water can act as both an acid and a base. That gives it some kind of interesting properties. So we're going to do a whole section on acids and bases just to make sure you're on solid grounding with that. So we'll talk about it more than how it dissociates and into what. Water constitutes a big portion of the body. Don't worry about knowing these numbers, but it's our solvent for so many things. So we're going to see it in so many reactions, so many steps, so many processes, so many everything. So there's several places in this class where we do something or start something, and we go up to the edge of physiology. Where that line between biochemistry and physiology is kind of a big, wide, gray line. So within the curriculum, we kind of sort it out. One class will go to this point, and the other one will pick up. So what we're going to talk about now is the cell a little bit and osmotic processes. So we'll go there in a minute. What we're going to talk about is moving fluids in and out of the cell. So to have that conversation, we've got to talk about fluids. So we can have fluid in the cell, and that's called the intracellular fluid. We can have fluid outside the cell. That's called the extracellular fluid. So in the cell, we have way more potassium than sodium, about 11:1 ratio. Outside the cell, we have way more sodium than potassium, about a 14:1 ratio. What we do is a lot of things where we'll move sodium in and potassium out and cause something to happen, whether it's open a transporter, cause an action potential, all kinds of things. So you're going to see that not only in this class, you're going to see that in all of your physiology classes. So you'll come to that and you're going to move ions different ways and for different reasons in physiology. Our part right now is we're going to move water. So we have the intracellular fluid, more potassium, extracellular fluid, more sodium, and the extracellular fluid is made up of two components. So the extracellular fluid is partially plasma and partially interstitial fluid. So what the interstitial fluid is the fluid that stays put. It just stays put, kind of hangs out in between the cells, allows you to pass nutrients and other things you want to pass from cell to cell. The other 1/4 of the extracellular fluid is the plasma, part of the blood. It circulates. So you also talked in general chemistry about ions. So ions are an atom or a molecule that has lost or gained one or more valence electrons. So we have a charge there because of the electrons. If we have a negative charge, it's an anion. If we have a positive charge, it's a cation. So it's easy to forget this because let's say we have a molecule like sodium chloride. We write NaCl, and it's just what we do the way we do it. But don't forget that when sodium chloride is floating around in water, it's not floating around as sodium chloride. It's floating around as sodiums, and it's floating around as chlorides. So we're going to talk about dissociation constants and what that means, what we're going to do with those when we get to the acid and base conversation. So like we said, plasma makes up about 1/4 of the extracellular fluid. It's the part that moves. The main cation is sodium, the main anion is chloride. We're going to have some other cations around, and physiology we'll talk about those. Potassium is the main cation in your intracellular fluid. The main anions are proteins. So we'll talk about the proteins, we'll talk about what you're going to do with those. Got a little bit of sodium, a little bit of calcium, a little bit of magnesium. What you're going to notice is most of your conversation with ions in both biochem and physiology is calcium, magnesium, sodium, and potassium. Where they go and what they cause by where they go, moving into the cell or out of the cell. Okay, the next place we're going to go is we're going to talk about osmosis. It's a type of diffusion where we can move water through a semi-permeable membrane to even out a concentration. So the water will move to the area of higher concentration up the solute gradient to even it out. So we're not going to use numbers with our concentration, but don't forget osmolarity, osmolality, they're all measures of concentration, just using different units. So like I said, we're not going to do the calculations, so that's not important, but we are going to draw some pictures and do some definitions. So we have 4 parts of words we're going to use as we go through and do this. So you're going to do, again, we're going to go back to our biochem terminology. So we have 2 prefixes. We have hypo and we have hyper. So hypo is not enough. If I have hypothermia, my temperature is too low. You know, that's like Floridians when it's 60 degrees out. Or, and I'm one of them now, so I can say that. Or hyper is too much. You have hypertension. Your blood pressure is too high. And we're going to put those on the end of two roots. The roots of volume or tone. So we're going to turn those into adjectives. So we're going to have tonic or volemic. So tonic is going to be, I don't know if I want to dash there, probably not. Tonic is going to be the ions. Volume is going to be the water. So let's back up to something for a second, because this gets turned around kind of easily. So when I'm dissolving something, don't forget that dissolve. The solute dissolves the solvent, or dissolves in the solvent, I'm sorry. So the solute dissolves in the solvent. So the solute is your ions, the solvent is the water. So let's talk a second about a concentration, and it's kind of a convention thing. If I'm talking about a concentration, it might be parts per million, milligrams per liter, whatever. So let's use milligrams per liter. We're talking about milligrams per liter. We're talking about, we're putting the solute, how many milligrams of solute in how many liters of solvent. That's just our convention. We say how much solute per solvent, how many milligrams per liter. We never say how many liters per milligram. However, in our conversation that we're about to have, we are going to kind of turn it around, and I'm bringing that up so that when you see it turned around, you recognize that and you're okay with it. So what we're going to do is also have a conversation about equilibrium. Here's the thing with equilibrium. We're always moving towards equilibrium. That's pretty easy. But not all equilibriums are good equilibriums. So sometimes we'll go to equilibrium, it'll be a bad equilibrium, then we'll adjust something and go to a new, better equilibrium. So we're always going to equilibrium, but just because we're going to equilibrium doesn't necessarily mean it's a good equilibrium. So we're going to use that too in a minute. So what we're going to do is we're going to describe a couple of situations. So what we're going to do is I'm going to have a cell. So I'm going to have some intracellular fluid, and I'm going to have my extracellular fluid. I'm going to have some ions. So what we're going to do is we're going to talk about a situation that will be a deviation from equilibrium that will cause diffusion, an osmotic process to happen to go to equilibrium. The catch is it's just not a good equilibrium. So I'm just going to use an X for my ions, kind of like the variable in math. And when you get to physiology, you'll talk about what ion will cause what, and you'll name them. And you'll have a reason for discussing that ion and whatever process you're talking about. And I'll put a couple ions in the extracellular fluid. So what I'm going to do is I'm going to use hyper and hypo and describe this situation. So this is a deviation from equilibrium, and I'm going to describe it. But I'm going to describe exactly the same thing 4 different ways. So I'm going to say the same thing, but I'm going to say it 4 different ways. So the first thing I'm going to say, and the order doesn't matter, is I'm going to talk about the ions. What I'm going to describe is what's going on in the intracellular fluid with respect to the extracellular fluid, or vice versa. So let's talk about ions first. In the intracellular fluid, I have more ions than I do in the extracellular fluid. So I have a hyper, too many, tonic ions in the intracellular fluid. When I go to the extracellular fluid, I have not enough ions with respect to the intracellular fluid. So I have a hypo, not enough, tonic ions, extracellular fluid. So I'm saying exactly the same thing. When comparing them to each other, I have too many ions in the intracellular fluid, or I don't have enough ions in the extracellular fluid. I can do the same thing with the water. When I look at the extracellular fluid, I have too much water, hypervolemic. compared to the intracellular fluid. The intracellular fluid, I have too little water. Hypo, not enough water, as compared to the extracellular fluid. So what I've done here is I've said exactly the same thing 4 different ways. Too many ions inside the cell is not enough ions outside the cell. Too much water outside the cell is not enough water inside the cell. So these 4 terms are saying exactly the same thing. They're saying exactly the same thing, describing a deviation from equilibrium. So then we said the whole world is moving towards equilibrium, including my little cell here. So what's going to happen is we're talking about osmosis. We're moving the water to level out the concentration. So to level out the concentration, we're going to move water into the cell. So we'll move water into the cell, which is going to swell the cell up, make the cell big with all that extra water to even out the concentration. Once I do that, I have an equal concentration. I'm not hyper or hypo anything. But once I do that and swell that cell up, what I'm actually describing is edema. So, what caused my edema? What caused my edema was a hypertonic ICF. What caused my edema was a hypovolemic ICF. What caused my edema was a hypotonic ECF. What caused my edema was a hypervolemic ECF. So they were the cause describing the deviation from equilibrium. But then I moved my water, went to equilibrium, swelling the cell up. I'm no longer hyper or hypo anything. I have edema. So that's my edema. Let's do it again, kind of the other way around. So this time, I have my intracellular fluid, I have my extracellular fluid, and I have a higher concentration of ions, again, whatever ion, outside the cell than inside the cell. So I have, again, this deviation from equilibrium. I'm going to say exactly the same thing 4 different ways to describe that deviation. It's kind of like saying my glass is half full or my glass is half empty. I'm saying exactly the same thing. I'm just saying it differently. Too many ions, not enough water. Too much water, not enough ions. Too many ions inside is not enough outside, and so on. So we'll do the intracellular fluid first. I have too much water, so I'm hyper in water, volemic ICF. Or too much water equals not enough ions. I'm hypo, ions, tonic, ICF. Outside the cell, I'm too much in ions, hypertonic. Or outside the cell, I'm hypo in water, hypovolemic. So again, saying exactly the same thing 4 times, 4 different ways. Too much, too little, water, ions. So 4 different ways of describing this deviation from equilibrium. So the whole world is moving towards equilibrium, including my little cell here. So what's going to happen is to go to equilibrium, water is going to move from the area of lower concentration to the area of higher concentration. Level this out. So I've got water moving out of the cell to give me equal concentrations. As I move the water out of the cell, I shrivel this poor little cell up. I pulled the water out, shriveled up the poor little cell, so I have equal concentrations now. When I have equal concentrations, I'm no longer hyper, hypo, anything. But what I do have going on is dehydration. So what causes dehydration? Hypervolemic ICF, a hypotonic ICF, a hypertonic ECF, a hypovolemic ECF. So for now and for what we're doing, the way you'll get questioned on this is very, very mechanically. Which of the following causes dehydration? You'll get one of these and three that cause edema. My suggestion to you would be draw it, because it's really easy when you're doing it in your head to flip a hypo. Or what causes edema, you'll get three of these and one that actually causes edema. And again, I would draw it. It's really easy to flip around. Or the other way you get asked is you'll get something like this. You have a hypovolemic ECF. What does it cause? And again, draw it out. You'll see water has to go one way or the other, and that will tell you edema or dehydration. So that's your mechanical question approach now, which I know is important because that's what you're worried about now. How you're actually going to use it, which is really the more important part, will be places like physiology. So you might be talking about, I don't know, the kidney, whatever. And you'll talk about a particular cell that's hypotonic in sodium, and this is what happens as a result. And you'll say, okay, hypotonic. That means not enough ion. We're talking about sodium. I don't have enough ion, don't have enough sodium in the cell we're talking about. So here's why whatever we're talking about is happening. So when you're actually using it, which you will in physiology and other classes, you'll break it down that way. And that's why we did it so mechanically. So you have the tools to say, okay, too much, too little, ion, water, and here's whatever happens as a result of that. Okay, so we're going to talk a little bit about the regulation of water balance. We're going to save a lot of this conversation for endocrinology in Try 3. The reason is you have more of the parts then and more of the pieces to put together. So water balance depends on a few things. It depends on antidiuretic hormone. Antidiuretic hormone will control your sodium, your water, your potassium, things like that. What it will make you do is either keep or get rid of water in the kidneys, because what it will do is make you keep or get rid of sodium, and the water will follow the sodium. The control of all this is through the hypothalamus. The hypothalamus is kind of the controller of a lot of things, or not kind of, with a lot of things. I put the kind of on because I almost said everything. Not quite everything, but a lot of things. And it'll control through the pituitary, most often the anterior pituitary. So we send signals based on what's going on, and the signal is release or don't release a particular hormone, in this case, antidiuretic hormone. So we'll come to that and we'll go through the steps with the hypothalamus talking to the anterior pituitary and so on, causing the release of antidiuretic hormone or not. We also have evaporative losses due to respiration and perspiration, kind of secondary with the regulation, but they do also regulate. We're going to leave the kidneys more for physiology and for endocrinology. But the little bit we'll talk about now will just be enough for you to relate it and connect it when you get there, because the connection sometimes is the hard part, putting the pieces together. So, really tiny change in the concentration of your extracellular fluid can cause you to release antidiuretic hormone. When you release antidiuretic hormone, that makes you thirsty. And physiology will talk about that mechanism. How you get thirsty makes you take in water to level out these concentrations. So anyway, we'll talk about some of it in endocrinology. You'll talk about more of it in physiology and tie the pieces together. Let's talk about diabetes for a minute. One of the challenges with diabetes is what kind of diabetes. And I'm saying what kind very, very, very on purpose. When we say diabetes and think about diabetes, we're usually talking about diabetes mellitus, mellitus, whichever way you want to say it, tomato, tomato. That's the one that's so common, results from insulin resistance, has a type 1 and a type 2. Some researchers talk about a type 1.5, type 3, Alzheimer's, glucocorticoid induced, and so on and so on. You're going to get diabetes to death in this curriculum. The reason you're going to get diabetes to death is that the prevalence of diabetes is going through the roof. Some researchers estimate that between 80 and 85% of the adult American population is insulin resistant. If that's the case, which it likely is, that means our incidence of type 2 diabetes is going to keep skyrocketing. Right now it's 11% of the population diagnosed. There's some pretty high estimates of how many people are undiagnosed, and it's climbing every year. So you're going to have type 2 diabetic patients in your office. You're going to have insulin resistant patients in your office. So that's our type 2. Type 1 is juvenile onset, still an insulin and pancreas story. So when we think diabetes, that's the road our heads typically go down. But there's another kind of diabetes. We'll talk about it in endocrinology and try 3. Diabetes insipidus. So nephrogenic diabetes insipidus can be a genetic disorder where the ADH receptor doesn't work. So now we're not talking about insulin resistance like we are with mellitus or mellitus. We're, in a way, talking about ADH resistance. So this is a whole different pathophysiology, whole different thing. Hormone we're worried about is ADH, different organ, different everything. So the ADH receptors are not working, we're not responding to ADH. So we're not able to respond to little changes in ion concentrations in the extracellular fluid. What's confusing about this is the symptomatology can be similar. You're thirsty, you drink a lot, so you urinate a lot. Very similar to the diabetes we're much more familiar with. So we could have normal pituitary function, and again, we'll talk about that. The hypothalamus communicates with the pituitary, so that communication can be fine. Communication from the pituitary can be fine. We can release antidiuretic hormone exactly the way we're supposed to, but the signal is not getting received properly in the kidneys. So we'll talk about this one some more when we get there in endocrinology. But probably the big takeaway right now for it is it's a whole different kind of diabetes, different hormone, ADH, not insulin. You tend to think of insulin, different function. We're nowhere near the pancreas. We're talking about the pituitary, talking about the kidneys with this one. So be careful, just don't confuse them. Question that often comes up, well, which type is this? Is this type whatever? No types. The types go with the insulin and the pancreas story. This is a no type. This is something entirely different. So we'll come back and talk about it. Okay, so that's as far as I wanted to get with water. And that's the end of this module. So at the end of the module, you're going to do a quiz. You'll have some activities to do. Then we'll move on to the next module where we're going to talk about acid and base, and we'll talk about enzymes, and we'll start getting into more biochemistry.